In this video, we'll discuss sections 1, 2, 5, and 4 of chapter 17 on spontaneity, entropy, and free energy. In this video, we will define each of those. First up, spontaneity. Although College Board prefers the term thermodynamically favored. If a process is thermodynamically favored, it can occur without outside intervention. That means without added energy. A thermodynamically favored process could be fast or slow, as thermodynamics doesn't give us any information about the speed of the process. That would be kinetics. Thermodynamics is concerned with heat and temperature and their relation to energy and work, so that allows us to predict the direction in which a process will occur. However, you need both thermodynamics and kinetics to fully describe a chemical reaction. You may recall this graph from earlier in the course. Thermodynamics allows us to say that the enthalpy change is negative between reactants and products, and so this reaction is exothermic. If a reaction is exothermic, it is likely to be thermodynamically favored or spontaneous. However, if the activation energy is high, and remember that's here on the graph, something that we might predict to be thermodynamically favored may not actually occur at a measurable rate, meaning that the process is under kinetic control. So it's not just about if something is endothermic or exothermic, because endothermic reactions can be thermodynamically favored or spontaneous as well. So that leads us into entropy, which we represent with a capital letter S. So enthalpy is H and entropy is S. Entropy describes the number of arrangements that are available to a system existing in a given state. The more arrangements that are possible, the higher the entropy. Nature will spontaneously proceed toward the states that have the highest probabilities of existing. And the driving force for a thermodynamically favored process is an increase in the entropy of the universe. So think about entropy as being positive. Let's talk a little bit more about the number of arrangements or positions that are available to a system and which arrangements have the highest probabilities of existing. Let's start with positional entropy. Of the three states of matter, gases have the highest positional entropy. If you remember, gas particles are very far apart, so they will have more positions available to them or more arrangements available to them than liquids or solids. Another way to describe that is to say that the matter is dispersed. In general, if we increase the volume of our gas sample, that will increase the entropy. There's more space for the gas particles and more arrangements are possible. And if we increase the temperature, we'll also see an increase in entropy for a gas. Another way to say that is that the kinetic energy is dispersed. Let's take a look at an example. You have a gas in the left chamber, and if you open the valve here so that a larger volume is available to the gas, you will see an increase in entropy as the gas fills both chambers. So the matter is dispersed, or there are more arrangements or positions available to the gas particles. Additionally, we should see a uniform distribution of the particles, so same number of particles in both chambers, because this position, this arrangement, has the highest probability of existing. If you're not convinced, let's take a look at just 4 particles. There are 5 different arrangements that are possible for these 4 particles. Either they're all in the left chamber, all in the right chamber, evenly distributed between the 2 chambers, or 3 on the left, 1 on the right, or 1 on the left, 3 on the right. Each arrangement has one or more microstates, and that's basically what's pictured here. With 4 particles in the left chamber, there's just one microstate that is possible. But when we do 3 particles in the left chamber and 1 in the right chamber, there are 4 different ways to arrange those particles. You can see A, B, C, and D each take their turn in the right chamber. When you get to 2 particles in each chamber, you have 6 microstates, or 6 ways to arrange those particles. And this happens to be the greatest number of microstates available to these 4 particles. So this will be the most likely arrangement, as we said in the last slide. As we work our way through the other arrangements, again, you see only 4 microstates with 1 particle in the left chamber, 3 particles in the right chamber, and 1 microstate with 4 particles in the right chamber. That leads us into the second law of thermodynamics. In any spontaneous process or any thermodynamically favored process, there is always an increase in entropy of the universe. That is the second law of thermodynamics. The entropy of the universe is increasing. The total energy of the universe is constant. That's the first law of thermodynamics, or the law of conservation of energy. But entropy is increasing. Let's apply the second law of thermodynamics to chemical reactions. We can look at positional entropy by looking at the relative numbers of gas molecules that we have in a chemical reaction. So the first example there has no gas on the reactant side and 1 mole of gas on the product side. So we should see an increase in entropy for that first reaction. In the second reaction, we have 3 moles of gas on the reactant side and only 2 moles of gas on the product side. So with less gas being produced, we should see a decrease in entropy. This means that the change in entropy for the first reaction would be positive, and the change in entropy for the second reaction would be negative. That leads us into the third law of thermodynamics. If you have a perfect crystal at 0 Kelvin, the entropy is 0, and that's what you see in diagram A. So remember, 0 Kelvin is when all particle motion has stopped. So nothing is moving, and this is where we get the lowest possible entropy. So we're calling that 0 entropy at 0 Kelvin for our perfect crystal. If we increase the temperature above 0 Kelvin, we see an increase in entropy, as shown in diagram B. We start to get some vibrational motion, and we'll see an increase in entropy here. There is actually a list of standard entropy values in Appendix 4 that represents the increase in entropy that occurs when a substance is heated from 0 Kelvin to 298 Kelvin, room temperature, at 1 atmosphere of pressure. And if we can look up the entropy values for the different substances in a chemical reaction, we can calculate the entropy change for the chemical reaction. This equation might look kind of familiar. We did this with enthalpy changes. So same idea. We're going to look up the entropies of our products, sum them together after multiplying them by their coefficients, and then we will subtract off the sum of the entropies of the reactants multiplied by their coefficients. This equation is in your reference packet, just like the equation for the enthalpy changes. Let's do a sample problem. We have some standard entropy values for the substances that are in the chemical equation at the top of the slide. We are going to calculate the change in entropy. So we're going to do products minus reactants. My two products are sulfur dioxide and nickel 2 oxide. I multiply each of the entropies by 2 because each of them has a coefficient of 2. And then I'm going to sum them. And now I'm going to subtract off the sum of the reactants. So always products minus reactants. So 2 times the entropy for the nickel 2 sulfide and 3 times the entropy for the oxygen. I'm going to sum those together. I get negative 149 joules per Kelvin. So we see a decrease in our entropy, and that should make sense based on the number of moles of gas that we have. Initially, we have 3 moles of gas, and then at the end of the reaction, we have only 2 moles of gas. So with a decrease in the number of moles of gas, we should see a decrease in our entropy. Finally, let's talk about Gibbs free energy, or G. This is the amount of work, and work is a force applied over a distance. So the amount of work that can be done by a thermodynamically favored or spontaneous process. We have an equation for Gibbs free energy shown here. This is in your reference packet. It ties together the enthalpy change and the entropy change along with temperature. That is what T stands for. So this equation can be really useful when you have a reaction that might be thermodynamically favored at low temperatures or high temperatures. This will help us figure it all out. When we calculate the free energy change, or delta G, we would like to see a negative delta G. That will mean that our process is thermodynamically favored or spontaneous. If we have a negative delta H if the reaction is exothermic, and a positive delta S if the entropy is increasing, we will always get a negative delta G. However, we can get a thermodynamically favored process under other conditions. We'll talk about that on the next slide. But remember, if we have high activation energy, even if something we might predict to be thermodynamically favored, it might not actually occur at a measurable rate. And again, we would say it's under kinetic control. So we just said we would get a negative delta G when we had an exothermic process along with an increase in entropy. So we would say it's spontaneous or thermodynamically favored at all temperatures. So no matter what you put in for T, you will get a negative delta G. And that's what we want to see for a spontaneous or thermodynamically favored process. When you have a negative delta S and a positive delta H, you will never get a negative delta G, no matter what temperature you put in there. You're going to basically subtract a negative, right? So you will be adding. And so no matter what the temperature is in Kelvin, remember no negative temperatures there, you will always get a positive answer. And so we will never get a negative delta G under these conditions, and then our process is not spontaneous or thermodynamically favored at any temperature. Now, if we have a positive delta S and a positive delta H, all right, so now pretend like we are still subtracting those two. We could still end up with a negative delta G if our temperature is high enough. So we'll multiply our delta S by a high temperature, and then that will give us a negative answer. So we'll get a thermodynamically favored process or a negative delta G only at high temperatures. And if the temperature is low, though, we will not. And then the last case is if you have a negative delta S and a negative delta H. Again, we're going to be adding here. And so we can keep our answer negative if the temperature is low. So if we don't add enough to overcome that negative delta H, we can get a negative delta G still and the thermodynamically favored process. But again, it's got to be at a low temperature. So in this video, we've discussed entropy and Gibbs free energy and the idea of thermodynamically favored processes. We will continue in future sections talking more about Gibbs free energy.